Hello, class. Um, I'm here with Bugger. Bugger had a tough night last night. I think his ear is hurting him, and you can see he's trembling. Poor guy. Um, yeah, his right ear is bugging him. So he's being really pathetic today. So I think I'm going to put him up here. You just stay there. Oh, Bug! Lay down. Lay down. We're going to have to take him to the vet. He's Bug. The thing you have to know about Bug is he's really good at being extremely pathetic. He can be really pathetic sometimes. So I'm a little bit sad. All right, so before we get started here, I wanted to talk to you guys about a couple of things. First of all, the quiz for this week is simply to turn in your, okay? So there's no additional work for this quiz. All you have to do is turn in the daily items. You can still work in groups of 4. Just slap 4 names on it. I'm not going to check them for correctness. I'm just going to check, did you turn something in? Okay? Another thing I wanted to say about the daily items is if I'm, I just wanted to say if you don't complete the daily items, if you just do a little bit, just do what you can. Okay, I don't want to cause you any anxiety. So just, don't work too much. If you feel like you're done with physics for the day, then just stop. I'm not going to hold it against you. Next thing I wanted to talk about is the second tech check-in is just because the viewership has been declining, and I want to see whose parents I need to call, whose houses I need to call, that sort of thing. All right. So that's my news for this week. So we're going to do some paper 2 questions. All right. So the IB exam has 3 parts: paper 1, paper 2, paper 3. Paper 2 is where the bulk of the points for the IB exam come from. Okay, it's the free response section. You have to answer all the questions, so it's going to cover the full range of the course. I have selected some questions for us to do from the, let's see, this is, you can see it's May 2019. It's time zone 1. Okay, so I just chose a random 5 and 6. Okay, and question 2, silicon 30. So I kind of tried to choose from 30 by the process of beta plus decay. Write down the nuclear reaction that represents this action. So, okay, so we start out with silicon 3014, and it's going to become phosphorus 30. Okay, but we have beta plus decay. Now, if we think about beta plus decay, remember the top row of numbers is the nucleon number. Now, a beta plus is an anti-electron. Electrons don't live in the nucleus, so the number for this one would be 0. Be careful about, whenever they talk about beta decay, you have to remember the neutrino or antineutrino. Now, because a beta plus is an anti-electron, it's going to come out with a regular neutrino, a regular electron neutrino, which is 0, 0. Has no charge and it's not a nucleon. If it were a beta minus decay, beta minus is an electron, which is a particle, and so that would come out with an anti-electron neutrino. The reason for this is we have to conserve lepton number. Okay. Number 2 says, sketch the Fineman diagram that represents this reaction. The diagram has been started for you. One of the things I see here is that time is flowing vertically. So that's different from what I had for my Fineman diagrams. There are different conventions. I've always learned, when I was in grad school, I studied quantum field theory, and we always drew our time going horizontally in our Fineman diagrams. So different strokes for different folks. So we're going to draw it with the time going vertically. So we have time is going vertically. We have an up, down, up. Up, down, up, that is a proton. And in the end, we're going to have up, down, down, which is a neutron. Okay? So wait a second. Oh my gosh, I totally goofed on this one. It says phosphorus is formed from silicon. So I totally goofed. I'm sorry. I had it backwards. This should be phosphorus, and this should be the silicon. My bad. Notice how this doesn't even, 14 plus 1 equals 15. So the thing I had drawn originally was, wouldn't even satisfy conservation of charge. So kudos to you if you caught that and you were scratching your head. So I'm going to draw the Fineman diagram. So we have a proton is becoming a neutron. And so we can see that the charge of this up quark here went from plus 2/3 to minus 1/3. So the charge went down. So there has to be a W plus boson that escapes. So W plus boson gets spit out. That's a weak force carrier. Why does it have to be a W plus? Because 1 minus 1/3 equals 2/3. Now that W plus then splits into a lepton and an anti-lepton. And so this is an anti-electron, which is the beta plus, and then we have the electron neutrino. So that would be the Fineman diagram. All right, part 3. Energy is transferred to a hadron in an attempt to separate its quarks. So what is a hadron? A hadron is a particle made of quarks. Okay, and basically we have this thing called confinement, Quark confinement. By the way, one of the things about doing the IB questions is it sometimes it reveals things that I forgot to teach, and I forgot to teach what Quart confinement is, so I'm going to teach it right now. So Quart confinement basically means that quarks cannot exist or cannot be observed alone, no matter what. It takes an infinite energy to separate quarks. Okay? So notice how it says in an attempt to separate its quarks. Okay? So I would say the attempt will fail because it takes infinite energy to separate a single quark. Okay? So quarks like to come in groups of 3. They like to come in groups of 2, but you can never see a quark by itself. And that's called Quark confinement. It's always confined. Individual quarks are always confined into groups of 2 or 3. Actually, one thing that was observed recently is something called a pentaquark, which is actually a bound state of 5 quarks. So you can also have pentaquarks. As far as I know, you can only have 2, 3, or 5 quarks together. All right. The Standard Model was accepted by many scientists before the observation of the Higgs boson was made. Outline why it was important to continue research into a topic once a scientific model has been accepted by the scientific community. I'm just going to answer this verbally. So basically what happened is the Higgs boson was the only particle in the Standard Model that had not been observed. Okay? So everyone thought that it was going to be observed, but it hadn't actually been observed. So they kept doing experiments. It's important to verify scientific models. Do experiments to verify and re-verify the model. And the other reason I would say that it's important to continue research is when you continue to do research, you're studying the model in more detail, and by continuing to do research, you find the places where the model doesn't work, okay? And so that's actually a good thing because it keeps physicists employed. So when a model doesn't work, people actually get excited. They say, ooh, that means new physics that we didn't understand before. All right, so physicists would be excited if the Standard Model was incorrect, because it would mean new physics. Unfortunately, the Standard Model seems to be correct. So we haven't done an experiment yet that has broken the Standard Model. The next question I'm going to do is question number 3. A beam of microwaves is incident normally on a pair of narrow slits. S1 and S2. When a microwave receiver is placed at W, which is equidistant from the slits, a maximum of an intensity is observed. The receiver is then moved towards Z along a line parallel to the slits. Intensity maxima are observed at X and Y, with one minimum between them. W and Z, or W, X, and Y are consecutive maxima. Explain why intensity maxima are observed at X and Y. So I would say that there is constructive interference between S1 and S2. Okay? I would say something along those lines. The distance from S1 to Y is 1.243 meters, and the distance from S2 to Y is 1.181 meters. Determine the frequency of the microwaves. So the first thing I would do is we need to figure out the wavelength of the light. And so I taught you guys an equation. It was delta R equals n lambda for constructive interference. Okay? Hey, Christian. So, now one of the things we notice here, going back to this, the W is the n equals 0 maximum, okay? X is the n equals 1 maximum because it's the next maximum. And Y is the n equals 2 maximum, okay? And then our path difference would be 1.243 minus 1.181. So this is an equation for lambda that we can solve. Okay. So 1.243 minus 1.181 divided by 2. That gives a wavelength of, I can't even read it, 0.031 meters. Then I'm going to use the fundamental wave equation, V equals lambda F, to solve for the frequency. It's the velocity. These are light waves, electromagnetic waves, so the velocity is 3 times 10 to the 8th, and lambda is 0.031 times the frequency. It's going to give us the frequency. That gives us 9.6 times 10 to the, actually more like 9.7 times 10 to the 9th hertz. Okay? C. Outline one reason why the maxima observed at X, Y, and Z will have different intensities from each other. So going back to the this drawing, waves, as they travel, as they spread out, the amplitude of the waves gets smaller. Okay, just like the sun's light. Okay, the farther away from the sun you get, the less the amplitude of the waves from the sun. Okay. So if we look at W here, W is closest to the sources. X is a little bit further from the sources. Y is a little bit further from the sources still. Z is even further still. So basically what happens is, even though there's constructive interference, the two waves that are interfering constructively are smaller the further the point of observation is away from the sources. Okay? So I would say that the amplitude of the wave goes down as the distance from the sources increases. Okay? So let's see. Whoop, and that's it. We did our questions for today, or I did my questions. You're going to do your questions later on. That's all I have for today. Thank you for watching, and I hope to see you on Discord. So have a great afternoon. Bye now.